Okay, pre-calc classes, this is the second part of section 2.4. Today we're going to talk about rational zeros theorem, which is finding all of the possible zeros that are rational at least. And then we're going to talk about upper and lower bounds. Basically, to find all of your possible zeros, rational zeros I should say, all we want to do is we want to take the lead coefficient. Whoops. Pen. There we go. So here's your lead coefficient. Okay, and here's your constant value. And what you're going to do is you're going to take the factors of the constant and you're going to divide by the factors of the leading coefficient, which they denote by P over Q. P are the factors of the constant, Q are the factors of the leading coefficient. For example, and you can see here what it says, possible rational roots, factors of the constant, which is P, and then the factors of the lead coefficient, which is Q. So it gives us a polynomial here, and they want to know what the possible rational roots are. So you take your constant term, which is positive 6, and it really doesn't matter whether it's positive or negative. And the factors of 6 are 1, 2, 3, and 6. Okay? So plus or minus signs have to go in front because we always have to account for negatives. Okay? So here are the factors for the constant term. Here is also now, here's our lead coefficient, okay? Well, that's our leading term, x to the third. There's no number in front, so we assume there's a 1. So our lead coefficient is 1, and our factors are plus or minus 1. So then we take each factor of the constant, and we divide them by the factor of the lead coefficient. So in this case, we have 8 possible rational roots. Plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 6. So when it says to find the rational zeros of this particular function, okay, what we want to do, we want to do our P over Q. Here's our constant term is just 1, so it's plus or minus 1, divided by the factors of the lead coefficient, plus or minus 1. So we have 2 possible rational zeros at plus or minus 1. So plug in 1. And actually, if you think about this for a second, let me erase this. What are we looking for? We are looking for when we hope that f of 1 equals 0. So we're going to take 1 and plug it in. So 1 to the third minus 3 times 1 squared plus 1. Well, 1 minus 3 plus 1 is, let's see, negative 2 plus 1, negative 1. Now, we wanted this to be 0. It's not. Okay? So that means that 1 is not a rational root. Do the same thing with negative 1. Do f of negative 1. We want to find out if the remainder is 0. Remember, the remainder theorem says take the number, plug it into the function. So negative 1 to the third power minus 3 times negative 1 to the second plus 1. Negative 1 to the third is negative 1. Negative 1 squared is positive 1 times negative 3 is negative 3 plus 1. So I get negative 3. Well, that's not 0, so that means that negative 1 isn't a rational root. So now you're sitting there saying, okay, well, there were only 2 possible rational zeros, or rational roots. Roots and zeros means the same thing. Okay? Now what? Well, here's what that means. That means there are no rational, excuse me for a second. I'm going to abbreviate. There are no rational zeros. RZ stands for rational zeros. Okay, there are no rational zeros. So what that means is graph. So graph it. Obviously use your calculator to graph it. And then find what the actual zeros are. Now what you'll find is that the zeros are actually irrational numbers, not rational numbers. Okay? So really for this problem, guys, I guess you don't really have to graph it because it was specifically saying what are the rational zeros? Well, the answer is there are none. So the answer is no rational zeros. Okay? If it just said to find the zeros, then you could graph it and find the find the places where the graph crosses the x-axis. Find the rational zeros of this function. So here's our constant term. So our p is plus or minus 1, plus or minus 2. Those are the factors. Here's our lead coefficient. So plus or minus 1, plus or minus 3. Now, when I go to divide these, I'm going to take each p and divide by the first factor of 1. So I have plus or minus 1, plus or minus 2. Now I'm going to take each of these and I'm going to divide by the second factor. So I have plus or minus 1/3, plus or minus 2/3. Okay? So there are our possible rational zeros. So there are 8 to choose from. Okay? Now, you can take the numbers and plug them into the function like I did in the last problem. Okay? We could also do this. We could also do synthetic division. Okay? So I'm going to start with 1 and put 1 in the box. Here are my coefficients. I am really not going to have any room for this. Hopefully this works. So bring down the 3, multiply. Add, multiply. Add, multiply. Okay. So we get a 0 remainder. So what that means is one of my rational zeros is x minus 1. That's one of my answers. Okay. Now, 3, 7, and 2 are now the coefficients of my new polynomial, 3x squared plus 7x plus 2. Okay. Now, that equals 0. Now, these are not the same zeros, but you're solving that polynomial. Now remember, when you do synthetic division and you get a 0 remainder, the resulting polynomial is 1 degree less than your original. Now, a couple things you could do. Notice the constant term and the lead coefficient are the same as they were up here. So your P over Q still counts. Okay? So there's a couple ways you could go from here. Once it's a quadratic, you could factor it. You could use the quadratic formula, okay? However you want to go about it. Or you could do synthetic division again, okay? It's completely up to you. But I will tell you that probably your best bet is to either factor or use the quadratic formula, okay? But again, it says rational zeros, so maybe we should just use the P over Q. Let's just use P over Q. If it was just finding the zeros and there was no restriction on it, then you could use factoring and quadratic formula. I apologize. But since they want the rational zeros, we should stick with these numbers. I'm going to try -1. So 3, 7, 2. Bring down the 3, minus 3, add them. Okay, that isn't 0. Doesn't work. By the way, you notice all the coefficients are positive. That probably means a negative number is going to wind up working here. So that doesn't work. Sorry guys, I don't have a lot of room here. So now I'm going to try -2. So 3, 7, 2. Bring down the 3, multiply, add, multiply, add. Oh, now look at this. So we get a 0 remainder. So that means that x equals -2 is one of our answers. Now notice these answers are coming from this list right here. Well, what's left? Remember, your resulting polynomial is going to be 1 degree less than the previous one. Well, the previous one had degree 2. So 3x plus 1 equals 0. Now, solve that for x. Now you can just solve it. -1 divided by 3. So x equals -1/3 is the third and final rational zero. And notice how all 3 came from this list. Upper and lower bound basically means this. We can find an interval, okay? We can find an interval that we can say all the rational zeros are, or real numbered roots, excuse me, all the real number roots are between these two x values, okay? Here's how we do it. If we use synthetic division to divide f of x by x minus b, b is a positive number, okay? And we obtain a third row containing no negative numbers, so all the numbers underneath, so all of these numbers right here are positive, then b, this number right here, is an upper bound for the real roots of f of x equals 0. So what that means is there are no real roots that would be higher than whatever that b number is. Now for the lower bound, we divide f of x by x minus b, where b is negative. This time b is negative. And our third row, the numbers are alternately positive and negative. So it goes positive, negative, or negative, it just alternates signs. Then b is a lower bound for the real roots, which means there are no real roots that are smaller than that b term, okay? Now, in determining whether the signs alternate in the third row, zeros are ignored. Okay, so it says prove that all of the real zeros of f of x equals, and then it gives you the polynomial, must lie in the interval -2 to 5. So, put -2 in the box. Write out your coefficients. Bring the 2 down, multiply, add, multiply, add, multiply, add, multiply, add. Now, again, we're not looking for a zero remainder, guys. We're not looking for that. What we are looking for is if -2 is the lower bound, then that means that these signs must all alternate down here. And as you can see, they do. Positive, negative, positive, negative, positive. So they alternate, which means -2, so therefore, triangular dots, therefore, where's that dot? Therefore, -2 is a lower bound. Now, for 5, the upper bound, now we put 5 in the box. I'm really not going to have room here, am I? No. We need to find a smarter way to do this. So there's your -2. Now we try 5. Sorry about this. So 5 goes in the box. So 2, -7, -8, 14, and 8. So 2, bring it down, multiply, add, multiply, add, multiply, add, multiply, oh boy, 245. That's 253, by the way. Look at that. All the signs are positive, right? Well, it said in the previous slide that if all the signs are positive in the third row, well, therefore, triangular dots, 5 is an upper bound, okay? So that's how you prove it. You just take the two numbers, put them in the box, and then just determine what the signs are in that third row. It's actually pretty simple. Last one. It says find the real zeros of a polynomial function. It says find all of the real zeros of that function. Now, if it's me, I graph it. And then find the zeros. Okay. I mean, that's really all I would do for that. If there's an alternative method, we'll show you. You can do the rational root theorem. In other words, you can do your P over Q if you want. Okay, but you don't really have to do that if you can graph it on your calculator. The only time I would do P over Q is if it says find the rational zeros. Then you've got to use P over Q. If they just want the real zeros, guys, you can just graph it and find the zeros on your calculator. Okay, and that'll do it. So if there's any questions, make sure you see me, and we'll get back after it tomorrow.